Hello, welcome to Regression Analysis in R by me, Dr. Alan Brain. This is a quick, simple introduction course for those people interested in producing regression analysis in R. So what is regression? Regression is used when we have reason to believe that changes in one variable causes changes in another. The simplest kind of causal relationship is a straight line relationship, and this can be analysed using linear regression. This fits a straight line with the data using least squares method. It gives the values of a slope and intercept that define the line when we use the equation y equals mx plus c. The data used for this presentation is available at www.drbrainstats.com, and this presentation complements the book. So, simple linear regression. We want to test if there is a relationship between sponge thickness and its liquid absorbency. We have designed an experiment with different levels of sponge thickness with the amount of liquid is absorbed. So within R, we're going to create our vectors and create a simple linear regression. We're going to create a graph with labeled axis and title. So now we come to the solution. I am not going to read out code, so please just pause the slide whenever you feel you want to, so you can just see what it does while I just briefly explain what we're doing. Now the first part just creates our vectors. The first vector is called sponge and the second is called absorb. The second part creates a new file that contains our results called linreg. And our final part produces the results, which we'll see on the next slide. R provides us with a lot of information, but first of all, we just want to solve our y equals mx plus c. To do this, we need to look at the estimates. We can see first of all our intercept, which is 0.0668, and the value we need to times sponge thickness, which is 0.1392, to get our absorbance, which is our y. Straightforward. But we've also got extra statistics we need to consider, which is our t statistic, which we have here. So we need this to satisfy the 5% rule, which as we can see, it does. So our next stage is to know whether this model is any good. This brings us to R squared. R squared is a measure of goodness of fit of simple linear regression. The value R squared is a fraction between 0 and 1 and has no units. And as a rule of thumb, an R squared value over 0.7 signifies a good fit. So now we go back to our results and we see that our R squared is labelled multiple R squared in our results, and it gives us an answer of 0.9095. So this tells us that it is a very good model and we should be able to use our linear regression equation with confidence. So for every millimeters of thickness, we should expect it to absorb 0.1392 milliliters more substance plus 0.68 milliliters. So if someone asks us the question, how much absorbency should we expect from a sponge that is 10 millimeters thick? We can provide the answer using y equals mx plus c, and the answer is 1.4588 milliliters. So our next stage is to create the plot. As we here with R, it's just a simple plot command. And to get our straight line, we need to use the command abline. Again, pause this slide whenever you feel you want to. Our next stage is to investigate multiple linear regression. It's a rare occurrence when we just have one variable to predict an outcome with confidence. When we use more than one explanatory variable to predict the outcome, we call this multiple linear regression, where y is independent, c is the intercept, mx, xp are the independents or the explanatory variables, and the error term. When developing models, the error term value is very close to 0, so we tend to ignore it. It is only here for equation accuracy and won't be considered further on. Also on the slide is an equation which other people may be more familiar with. Which now brings us to measurement. For a multiple linear regression model, we need to look at the adjusted R-square, because the R-square will increase as more variables are included in the model. This is an adjustment of the R-squared that penalizes the addition of extraneous predictors in the model. So now we go to an example of a multilinear regression. Hopefully you have a file called multi, and this contains the following variables for a sample of 19 companies: the company name, the profit, growth, and PER. Our first example involves constructing a multiple linear regression model to predict PER from profit and growth. So here's our solution. As you can see, it's very similar to our simple linear regression, but now we've got the extra variable growth, which has a plus sign added to it as well. And our results. As we see, using the estimates, the multiple linear regression is 5.56, which is our intercept, plus 0.47 times profit, plus 0.2 times growth. As this equation uses two exponential variables, we have to use the adjusted R-squared for its performance. When we just R-square of 0.54, we may not consider using this model as it falls below the 0.7 mark. But if we lack an alternative model, then we should use it. This brings us now to our second example of a multiple linear regression. Hopefully you have a file called multi2, and this contains the first order of drinks consumed in a restaurant or bar based on the first 31 days. Today is the day of the month. X1, average price of drink. X2, drinks ordered. X3, average daytime temperature in Fahrenheit. And Y, drinks remaining. Now we want to construct a multiple linear regression model to predict the amount of drink remaining from X1, X2, and X3. Again, the code is very similar, just using Y, and then X1, X2, X3 separated by the plus sign. Our results are straightforward. You can see the coefficients. And so our equation is 2.134 minus 1.021 times x1, 0.216 times x2, plus 0.034 multiplied by x3. As this model has three exponential variables, we use adjusted R-square, which is 0.68. And with a value close to 0.7, we can consider using this model. From our results, you may have noticed that the t-statistic for the variable x1 was greater than 0.05. So therefore, this variable fails our t-test. So therefore, again, we need to create a model without x1, which now gives us a completely new formula. So our predicted drinks remaining is now minus 1.06 plus 0.232 times x2 plus 0.035 times x3. And as you can see, the adjusted R-square has not reduced significantly, falling from 0.68 to 0.67. So although we have removed one variable from the model, it hasn't really affected the performance. Which now brings us to sequential approaches. Variable selection techniques tend to cause arguments among data scientists, statisticians, which I will not delve into here. There are always people dismissing procedures no matter what field you're in. I only mention this so that you're aware of this argument. There are three main sequential approaches: forwards, backwards, and stepwise. We just did a quick example of a backwards sequential approach. More information is available in the book. It is quite common to have a mixture of categorical as well as continuous variables in a regression model. So this section shows us how to use categorical variables within a model. A CSV file called Categorical contains 19 companies with the following variables: company name, profit, growth, PER, and its industry. The industry has three categories: financial, utilities, and computing. So we can use this data to construct a multiple linear regression model to predict PER from profit, growth, and industry. Our solution. Again, our code should look very familiar. We just imported the data. lm is a command to create the model. The only major difference now is that we've had to put the word factor around the word industry. This tells R that the variable to follow is categorical. With the industry being numerical, if we had not done this, then we'd have treated industry as a continuous variable. So now this is our results. With the category variable included, each bin has been given its own score. You may notice that industry 1 is missing. This has been given a value of 0. Unlike continuous variables, where we multiply the explanatory variable by the estimates, for categorical they just have a fixed value. But as we can see, results have shown us that profit is not a good explanatory variable to predict PR based on this T statistic. Our next stage is to model again without the variable profit. Now, from our new model, we can notice that growth has a T statistic greater than 0.05, but it's not that much over. So we may want to remove this, but this is a personal choice. In this instance, we are keeping it so we can carry on to the next stage. Also, with a Deshidar square of 0.6317, this tells us the model is not strong, but could be used with caution. Finally, we are ignoring industry 3 T statistic as it's part of the industry variable. To be accurate, we should combine industry 1 and 3 together. Logistic regression. Logistic regression is used to calculate the probability of an event occurring. For example, a person responded to a direct mail or the customer defaulting on a loan. When considering a logistic model, we need to add up the model scores, as done previously, and then convert it into a probability, as will be demonstrated. The logit is a device for constraining the probability between 0 and 1. Our last exercise is to build a logistic model. Using the CSV file called logistic1, import this file and call it logistic1. This file has a binary response variable called sold, which is equal to 1 if the sale has been made, and 0 otherwise. There are 3 predictor variables: income, mortgage percenter, and tier. The variable tier takes the values 1 to 4. Tiers with a rank of 1 have the highest prestige, while those with 4 have the lowest. As our solution, as we can see again, the code looks very similar. Logistic mod, we've got our GLM code, we've got our equation. The only difference here is the word family equals binomial. This tells R that sold is binomial. And again, we use a summary to get our results. In the logistic results, we have the Z values, which you can treat the same as previously with the T values. As you noticed, R still uses the star system, and all the variables are predictive. So therefore, we can go straight to our linear equation. So score equals the intercept plus income multiplied by its estimate plus mortgage multiplied by its estimate plus the tier estimate. We've now added up all those scores. We have to convert it into a probability using the equation shown on the slide. So let's use ID1, which has a tier 3 as an example. I'm not going to work out all these numbers, but when you get our linear equation, the result is minus 1.568. Now to convert this into the probability, use the following methodology, which gives us a probability that the sale is 17.26 for ID1. This brings us to the end of an introduction to regression techniques using R. R allows you to attach the predictive scores to different sets of data, as is demonstrated in the book, but this presentation focuses on creating the scores and understanding the results. As mentioned before, further information is available in the book. Thank you for listening.